Hello, this is Mr. Adetta, and we're going to be discussing the potential and kinetic energy as it is seen on your standard roller coaster. So, on the next page, what we're going to do is we're going to define each of these positions as to how much potential energy and how much kinetic energy they have at each position. Now, you're going to notice similarities between some of the other systems that we've already witnessed, including the ball bouncing and the pendulum lab. So if you just remember some of the rules we picked up from there, you should have an easy time understanding this. So I'm going to do these positions in order, but unfortunately the way I explain everything works, I can't flip back and forth between this picture and the page you're going to be putting in your notes. So I'm just going to stay on the note page, and then we'll just kind of talk from there. So position A, at this point, you have 100% potential energy and 0% kinetic. So you have maximum height, but it's not quite moving, so it has 0 kinetic. But as the cart starts to go downhill, it will start to convert that potential energy into kinetic. So you'll notice that the height is decreasing, which means the potential energy also has to be decreasing. And since the potential energy is decreasing, and you can't lose energy, that means that potential energy has to be going somewhere. So that means it's being converted into kinetic energy. As the car continues down, it is no longer at a height. So at this point, you would say that it has 0 potential energy because it's at the lowest point of the track. But since all that potential energy is gone, it's not destroyed. It's just been converted into another energy. In this case, it's converted into kinetic. So if we lost 100% of potential energy, that means it has become 100% kinetic energy at this point. As the car continues down the track, it starts to increase in height. So if it's increasing in height, that means its potential energy has to start to increase again. Well, that potential energy doesn't come out of thin air. It's not created. And what is happening is that kinetic energy is being transformed into potential energy as it slowly climbs up the hill. Okay, on this page, we're just going to put in the notes for each of the positions. It's basically what I just stated on the previous slide, so you can just kind of copy these at your leisure. So on point A, we saw that the position shows all potential energy and no kinetic energy. So 100% potential and 0% kinetic. As I explained, since the car is at the highest point on the roller coaster, it has 100% potential energy. Now at point B, as the car starts to roll down the hill, some of that potential energy was converted to kinetic energy. So at this point, you would just call it about a 50-50 of each. So 50% potential, 50% kinetic. So half of the potential energy was converted into kinetic energy. Again, remember that in a system, the energy always has to equal 100%. So 50 plus 50 at this point is 100% still. So that does still account for all the energy in the system. Because remember, according to the law of conservation of energy, you cannot lose and you cannot create new energy, so the energy in a system has to always equal 100%. At point C, you have the bottom position of the roller coaster, which means there is now no more height, which means there's no more potential energy, because all of that potential energy has converted into kinetic energy. So you end up having 100% potential, 100% kinetic. And then finally, at the final position, as the car starts to ascend the next hill, you will see an increase in potential energy, and that potential energy has to come from somewhere, so it's coming from that kinetic energy. So the kinetic energy is being transformed back into potential energy as the car slowly makes it up the hill. If you remember also, kinetic energy is related to the motion of the object. In this case, you can look at it as speed. So the more kinetic, the faster the object should be going. So if this car is starting to go uphill and losing kinetic energy, then you would also assume that the car is starting to slow down. Which, if you've ever had to bike up a hill or walk up a hill or a steep incline, you understand that your motion does get slowed down because you have to, your energy is now needs to be more to actually ascend that hill. And so you will feel that slowdown as your kinetic energy is somehow compromised. Okay, on this page, all I want you to do is just draw a picture of a scenario that shows both potential and kinetic energy and label it appropriately. So if I wanted to do something really quick, let me see if I can draw something out real quick. There we go. So this is my picture of an apple falling from a tree. So in this particular picture, I am showing both potential and kinetic energy. Because I'm showing the potential energy because the apple hasn't quite hit the ground yet, so it has height. And then it has kinetic energy because it is actually starting to fall to the ground, so it does have some motion. So if you look at this apple as being in midair, that is an example of potential and kinetic energy. And as the instructions say, it says include a sentence that describes your image, so let me do that real quick. And there you have it, an apple in the process of falling from a tree. Okay. So once you get this drawing completed, you are done with this note section. If you haven't already, just make sure it's glued into your journal so it'll stay there where it needs to be. Thanks for listening.